Good. So it's my pleasure to invite Peter Müller to the workshop. So Peter has been a professor at ETH for the last, 10 years? 11?
13.
13 years, okay. Lucky number. So Peter's been a professor, he's been working very much in the area of program verification and making program verification usable, both on the theoretical side, developing these theoretical methods and logics, and then also building tools. So this is really something that's very much needed in the community. And today he'll tell us about Viper and various encodings inside it. So, go ahead.
Okay, thank you. So we've worked for a couple of years on Viper, which is a verification infrastructure for permission-based reasoning. So by permission-based reasoning, I mean that we support program logics that center around this notion of an access permission. The most famous example is separation logic in all its flavors, but there are also others like implicit dynamic frames or type systems of this flavor, like the Rust type system, for instance. So this infrastructure comes with a number of components. The heart of it is an intermediate verification language called Viper. And that language allows you to encode various verification problems. So different kinds of source programs, specification techniques, program logics can be encoded into Viper. And then what we can do in Viper, we can do modular verification of these programs. That means we can reason about the program one method at a time, which is important for scalability and to be able to make statements about library code and so on. And so in order to do this kind of reasoning, we have three backends that operate on this intermediate language. One is a verification condition generator, which translates Viper programs via an encoding into Boogie, which Ruslan developed, who is here. The other one is a symbolic execution engine, which executes the Viper program and directly talks to an SMT solver to solve queries. And the third one is an abstract interpretation engine, which we use mostly to infer specifications that can then be fed back into the Viper program and used by the other backends. Now the benefit of this is that, that building a new verifier for a new source language or verification technique becomes a lot simpler because you can basically write front ends by just translating your given problem into Viper. And then what you get out is a tool that users can use directly. They would interact with this front end, and the tool developers save a lot of effort because they can reuse this entire infrastructure underneath. But what I would like to focus on in this talk here is another application of Viper, which I think is equally important but often underestimated in the community. And that's that you can use such infrastructures also for prototyping. So you can work directly as a human on the level of the intermediate language and encode verification problems to get rapid feedback. For instance, when you develop new specification techniques, new program logics, then it's very useful to get quick feedback such that you can run many examples and that you can check your examples carefully. So what I will do in this talk, I will give you a very, very quick overview of some of the ideas behind Viper, really just a glimpse. And then I will talk about how we use Viper for prototyping in one particular area, namely to automate or to experiment with relaxed separation logic, which is a separation logic for the C11 memory model. As I already mentioned, Viper is centered around permissions. I will explain permissions here in terms of separation logic, even though what we use in Viper underneath is something slightly different, implicit dynamic frames. So as I hope many of you know, the key idea in separation logic is that you specify programs in terms of so-called points to assertions. So this kind of assertion expresses two things. It says, first of all, the current method has the permission to access x.f. And moreover, x.f has the value v. So there are really two things encoded here. And this notion of a permission is very important because there's only one permission in a program execution at any given point in time. And so, for instance, you can use that to prove data race freedom. If you have only one permission and the permission can only be with one thread at a time, you automatically get data race freedom when you verify a program. So, of course, this only works if you actually check that you can only access a location if you actually have the permission. So that's why the rules for accessing the heap always require a suitable permission. So, for instance, a field update, x.f gets v here, requires to have some permission to x.f. We don't care about the value, that's what I mean by this underscore here, but we are allowed to access x.f, and then I can update it. That means I still have the permission, and now the location will have value v. Okay? And in order to make this compositional, in order to get modular reasoning, The key idea is that we can combine assertions, in particular the permissions in the assertions, using a so-called separating conjunction. So this star expresses conjunction in a particular way. It says this property P star R holds in a given heap. If you can split this heap or the permissions into two disjoint sets such that P holds in one of the portions and R holds in the other one. So you really divide the state up into two parts that are non-overlapping, that are disjoint. And that gives you very intuitive rules for reasoning. So for instance, one of the core problems in modular verification is framing. So the question is, what if I change some part of the heap? Which knowledge about the heap can I preserve across this change? And this is done in separation logic via this frame rule here. So assume you know that executing a statement S with a precondition P and a postcondition Q can be proved like this. Then you can always frame on an assertion R, provided that you use separating conjunction here. So why is this sound? Well, we know that S can access at most the memory locations for which P contains the permission, okay? And now if the permissions in R are disjoint from those in P, that means that S will not be able to affect R, and R will still hold afterwards. That's the intuitive idea behind that. And as I already mentioned, you can also use this for concurrency. So here's the most basic rule of concurrent separation logic. So we have a parallel composition of two statements, S1 and S2. And each of these statements operates on a certain set of permissions, here described by P1 and by P2. And as long as those are disjoint, I can execute the two statements in parallel, and I will definitely not get a data race. So that's a very simple idea. So now the question is, if you want to build an intermediate language that doesn't just automate one such logic, but a whole class of logics that follow these kinds of ideas, how do we do that? And so the core idea behind that is that the notion of a permission transfer is really central to reasoning in these kinds of logics. So here's a little snippet of a Hoare logic proof how you would typically reason in separation logic. So you would have some specification for a method M, and now imagine you want to verify a caller of M, right? So then what you typically do is, first you verify a triple about a call, like e.m. What I dropped here, just for simplicity, is that you would have to substitute formal parameters by the actual arguments. I just dropped that to keep the notation simple, but that's what you do. But then typically in the context where you make the call, you know much more, you have a much richer state than just P. So then you frame on some property R that will hold around the call. And basically what's happening here on a more operational view is this idea of permission transfer. If you just look at it from the perspective of the caller, what's happening from that perspective? Well, that caller needs to show that it has some permissions P, and it needs to transfer those to the method M so that method M can execute. And when M terminates, it promises some properties Q, some permissions Q back to its caller. So those things get transferred back to the caller. And some things like R just remain with the caller all the time, they get framed. But so the permission transfer here, that's the basic idea. The same holds for concurrency, right? So imagine again, you are in the context of this parallel execution here. So what you need to do is you need to have the permissions P1 and you transfer them to one of the threads. And you need to have P2 and you transfer them to the other. Now those threads are running, eventually they will terminate, and then they transfer Q1 back to you and Q2 back to you. So we have the same idea of permission transfer, and finally there's some property R that we can frame around the whole thing. So you see, permission transfer is really the key point in expressing what such a logic does. And so when we designed our intermediate language, we took exactly those operations and turned them into the most kind of primitive statements of our language. So we call those exhale and inhale, following what Rooston and I did earlier in Chalice. So exhale is a statement that takes an assertion. And what it does is it proves that all the logical constraints that are mentioned in this assertion P actually hold, so like an assertion. But on top of that, it checks that all the permissions mentioned in P are actually held in the current state, and then it gives them away. So it models the part of the permission transfer where you give something away, like what's happening when you make a call. The dual operation is inhale. Again, inhale takes an assertion Q, and it obtains all the permissions that are described by Q. And in addition, if Q also contains logical constraints, like x greater 0, you assume those properties. Okay? And that corresponds to the second half of the transfer when you get something. Right? We say you inhale it. So that means a call like this one can be encoded into Viper just by performing an exhale of the precondition followed by an inhale of the postcondition. And in particular, the framing just happens automatically. We don't have to do any extra proof step or infer frames or something like that. Anything that the caller will have and not give away during the exhale will still be available after the inhale. So that simplifies the proofs a lot. For those of you who are familiar with the verification literature, you can really see the exhale and the inhale as the permission-aware analogs of assert statements and assume statements in guarded command languages. It's like the primitives of permission-based reasoning. And now, based on these primitives, you can encode all kinds of interesting features. So, for instance, if you have monitors or locks, you can, in a source language, for instance, associate your monitors with a monitor invariant. Like this invariant here would express that this particular monitor protects the memory location this.bell. Okay, so basically it says it guards these memory locations, it contains the permission. And now intuitively what's happening when you acquire the monitor, then you transfer that permission from the monitor to the thread that now holds the lock. So now that thread can operate on the memory location, and when you release the lock, you give it back to the monitor. And so consequently, the encoding into Viper is completely straightforward, right? So the acquirer just inhales the monitor invariant, then you can play with the location, and then the release will exhale the location again. So this way you can encode all kinds of language features into very simple operations. So now what we've seen so far is like very, very classical permission-based reasoning, very classical separation logic, and in particular, as I already argued, this kind of reasoning guarantees data race freedom because there's only one permission to a location in the system. Only one thread can have this permission at any point in time. So you cannot have data races in the first place. But of course, as we all know, a lot of activities going on in writing racy code, fine-grained code, lock-free data structures, and so on. And of course, we would like to be able to reason about such programs as well. And the question is, well, can we do this in such a logic, or would we need a much, much richer logic in order to reason about such programs? So what I would like to do in the second half of my talk is to look at one particular logic, just at a few features of it, and just give you an idea how one can encode such a logic into Viper. The logic that I will look at is a logic for weak memory models. So it's not just for fine-grained racy concurrency, but even for weak memory, where, of course, you see certain behaviors that under sequential consistency you would never see. So here's the famous kind of hello world of weak memory. We have two variables that are initially 0, two parallel threads set A to 1 and B to 1, and they print B and A. And so under sequential consistency, you have three possible outcomes, but 0, 0 is not possible intuitively, because if you want to get to a print, you always have to assign a 1 first, so that then at least the other thread will see the 1. But under weak memory, you can also see 0, 0 as a possible outcome there. So what I will do specifically is I will look at one particular logic that works on the C11 memory model. And the C11 model is a complicated memory model. I will just look at two aspects here. So C11 has many different kinds of variables. So I will look at non-atomic variables. So non-atomic variables are like classical variables. So in particular, a data race on a non-atomic variable is considered an error. So during verification, we would like to show that there are no races on non-atomic variables. And then I look at one kind of atomic variable, and those are the atomic variables that are accessed via release, write, and acquire read operations. So these are specific read and write operations that allow you to access these atomic variables, and the speciality about it is that the memory model synchronizes the reads and writes. So what does that mean? So here's my running example. So I allocate a non-atomic variable and initialize it to 0. Then I allocate an atomic variable with a release acquire semantics, and it's also initialized to 0. And then I have two parallel threads. One of them assigns 5 to the non-atomic variable and then stores 1 into the atomic one, and the other one reads the atomic one, and if the value that was read is 1, then we want to prove that the non-atomic variable is 5. So this program is correct. What does correctness mean here? Well, it means two things. First, it means that the write axis here to the non-atomic variable and the read axis over there don't raise, because these are non-atomic variables, they're not supposed to raise. And moreover, the value over here will actually be 5. Okay, so this is actually an assertion that holds. So why is this correct? Well, in order to reason about such programs, you have to look at the happens before relation. Happens before is defined in this context via two separate relations. One is the program order, which is completely obvious. And the second thing is that these acquire reads and the corresponding release writes also add edges, so-called synchronizes with edges to the happens before. So we can look at different ways of executing this program. So for instance, one way would be that this load operation reads the value that was written over here. Okay? Then we get this extra edge over there. Okay? And now in this case, there's no synchronization between this axis and that axis, but well, we actually read the value 0 here, so we will not even access or execute the assertion, so that doesn't matter. It's correct anyway, we just see that what we read is not 1, and we'll just skip over the assertion. So that's the trivial case. The more interesting case is if you read the 1 over here, and now you see that this extra edge contributes exactly the important information to the happens before relation, because now this one orders the axis over here with the assertion over there. And because of this order that we get following these arrows, we know that there's no data race and the value will actually be 5. So what I will look at specifically is a logic called relaxed separation logic, developed by Victor Vafayadis and his co-author, that supports some features of C11. And the goal of what I want to show you here is not that this is the way how to reason about programs. I just want to show you that we can take such a logic for very advanced kinds of programs and encode them into Viper. So this relaxed separation logic is just one example. Our goal is to show that you could also pick other logics in this space and do the same kind of encoding and prototyping with it. So let me quickly show you some of the main ideas. So for the non-atomic variables, the situation is very simple. So the proof rules are exactly the rules of separation logic. When you allocate a variable, you get the permission to access it. In order to write it, you need the permission. In order to read it, you also need the permission. So this is just what you expect for non-atomic variables. So therefore, if we go to Viper, okay, so this is Viper. In Viper, we can encode this in a very straightforward way. So Viper has an object-based model. So we have objects with fields. In order to model a memory location that we have a pointer to, we just introduce a val field that and model every memory location as its individual object where the value is stored in the val field. And then later, I'll define a couple of macros to allocate, store, and load atomic variables. They are all empty so far because I have not shown you yet how to do this. And now down here, I encoded the running example. So what's happening here is I create the non-atomic variable and initialize it. I create the atomic variable and initialize it. And then I fork two threads by calling methods left and right. And so left, down there, writes the value 5 to n and then stores 1 in the atomic variable, and right performs the load, compares it to 1, and if it's true, checks the assertion. And you see that this doesn't verify. Left complains here that I'm trying to access val, but I don't have permission to do so. And well, in order to fix that, I can just give my method here a precondition and say I want access permission to n.val. So this is how we write access permissions in Viper. It's like the points to, just with a nicer syntax. And so now the error goes away. And so where does this permission come from? Well, it comes from the main function here. The main function allocated the memory location. So it has the permission, and it just transfers the permission over there, and we express this via this precondition. Explaining why the right branch is correct is a bit more difficult. So we get the same complaint here that we don't have permission to access n.val. But we could not just fix that by adding a precondition over there, because then both branches would require the permission, and the main method could just give it to either one or the other. The idea really is here that this one has it first, and when this one is done, then the permission travels over here, and then you can access the location over there. So what's the idea? How can we phrase this in the logic? So basically, the idea is that you can see these release-acquire operations like message passing. Releasing is like sending a message, and acquiring, reading, is like receiving a message. Whenever you send a message over to another thread, you can associate permissions with that message. So what does that mean in more technical terms? So what RSL does is it associates a location invariant with atomic variables. So here the location invariant is parameterized by the value of the location, and the idea is the assertion has to hold when the location has this particular value. So in our particular example, the idea is we want to say for our atomic variable a, the invariant is that we want permission to n, and n should be 5 if the value is 1. And otherwise, we don't care about any values, and we don't need any permission. Okay? And now the idea is basically, when you write this value 1, you better make sure that you establish this invariant of the location. So you need to show at this point that you have permission and that the value is indeed 5. But on the other hand, when you read the value, then you may use this permission. So it's very similar to the acquire and release of a monitor. You may use the permission, and you may use the information that the value is 5. And that's what allows us to prove the assertion. So how is this phrased in terms of proof rules in RSL? So when you allocate and initialize a release acquire variable, you must have the invariant of the value that you use for the initialization to begin with. And then you get two predicates. And these predicates you can see as kind of permissions to perform a write or a permission to perform a read. Okay? So therefore, when you want to do a store of a value v, you must have this permission to perform a write. And moreover, you must make sure that the invariant for that value v actually holds. Okay? And now at this point, you give up that assertion, that invariant, like giving it back to the monitor. Now you basically give it to the memory location. You send it away in a message. So what you are left with is still the permission to write, but this permission here is gone. You sent it to somebody else. And when you read, then you need the permission to read. And then when you read a particular value t, you get the invariant for that value, and you still have the permission to read, so you can. And now if we encode this, we see there's lots of extra machinery, but we need nothing on top of what we've already seen in Viper in order to encode that. So what I'm going to use here is I will introduce two fields, release and acquire, whose value I will never look at. So the only purpose of these fields is I want to be able to express I have the permission to perform a read, or I have the permission to perform a write. And then I introduce two macros just to have a convenient syntax to express that. Okay? And then I introduce yet another macro, q of v, for my invariant. So this is like on the slide. If the value is 1, then I want permission to n, and the value of n should be 5, and otherwise I don't care. And now with these definitions, we can easily give a semantics to allocation. So allocation, as we've seen, exhales the invariant, and then you get permission to read and write. Storing a value checks whether you have the permission to perform a write, and then gives up the invariant, so you exhale it. And loading a value checks that you have the permission to perform a read, and then you obtain the invariant, so you perform an inhale. Okay? And now with this, we have given a semantics to this C11 operations, and now we can go down to our program again, and so we see there are some problems there. It complains that I cannot do the store. Well, what I need to do is I need to say, well, if I want to do a store, I need to be able to write to A. So I just add this predicate here. And similarly, in the write branch, if I want to read, then I need the permission to acquire. And now Viper is happy and we have verified this program. So I think I'm running a little late, so I'll skip over some of the details. The encoding is a bit more complicated. In particular, what I've shown you so far is not completely sound, but I hope you believe me that we could easily fix that. And like Martin, I was ambitious and I thought I could show you that in the talk, but I won't. But anyway, we can do that. So what would I like, what's the point here? The point is that if you read papers about program logics, then typically the authors of these papers have two options to demonstrate that their examples really work. Most of them do a paper and pencil proof of typically a very small number of examples. Right? Of course, that's painful for the authors. It's also not so clear how trustworthy these proofs are. The alternative is that you encode the logic that you're currently developing into, say, Isabelle or Coq, and do a full-blown verification there. But that's very, very time-consuming. It's very trustworthy, but also very time-consuming, and you might not want to do this for every paper that you want to push out about the new logic. So what I'm trying to get across here is that there's a third way, namely you can take such logics and you can prototype them in an intermediate language, and that's much easier than performing an encoding in Coq, and it's much more reliable and faster in particular than performing a pen and paper proof. So here I've shown you that for a small example. Here's the actual proof outline. Basically the only things that I had to do in Viper in order to get the example verified is write the preconditions of the two parallel threads. So these things is basically what I had to do in Viper. And of course I had to encode the logic itself. But now I'm in a position where I can verify many more examples relatively quickly and can be relatively sure that the verification is actually correct. So let me summarize. It's important to recognize that intermediate verification languages bring a great benefit. Typically, people use it because they allow you to reuse a lot of infrastructure, verification condition generators, abstract interpreters, and so on. But there's this additional benefit that they allow you to prototype new ideas and get feedback very rapidly, which I think is super important. Viper is based around permission reasoning, like separation logic and implicit dynamic frames, so we can very easily reason about these kinds of programs. But what I wanted to emphasize in this talk is that we can also use much more advanced logics that prove things that are typically outside the domain of permission-based, or at least of traditional permission-based reasoning, and we can encode them nevertheless. If you're interested in finding out more, go to viper.ethz.ch, where you can try the tool online, access the sources, see lots of examples, and our papers as well. Thanks.
Am I correct when I say that this sort of reasoning, the separation logic will separate the permission part, let's say the linear part of it, from the actual logical contents of it? That's difficult to do with the start of it. Is that the reason why this happened like that? I have this condition also n is equal to 1. Somehow that's not permission-based, that's a logical.
Well, so the assertions can mix both, right? You can talk about values, you can have logical constraints, and you can talk about permissions. The connection is that you can only talk about the memory location if you also have permission to do so. So just writing an assertion saying x dot f equals to 1 is not a well-formed assertion, because without the permission to x dot f, you cannot even talk about its value. So typically, you need to combine both into one assertion, and then you can express whatever you want. Does that answer the question?
Yes.
Okay.
Thank you.
So I saw the previous example needed somehow tricky invariant that, or relatively tricky invariant that probably could have been synthesized, especially if I want to use Viper for a tool that uses a more advanced logic. So does Viper support any form of synthesis where I can put calls in the...
Right, so what we have at the moment, I mentioned these three backends, right? You can see them there. So the abstract interpretation backend, so that performs abstract interpretation in order to infer specifications, loop invariants, method preconditions, and so on. So that inference is not advanced enough to be able to handle, for instance, this particular example. But I mean, Jerome is working on that, Gracie. Yeah, Jerome is working on that, and this is clearly one of our top priorities. So now basically we have the infrastructure in place in order to check proofs in a sense, to make sure that things are actually correct. And now we want to increase automation. You might have spotted that I changed the title from automating to prototyping, because actually the automation is not that high as you saw in the demo. So there's still assertions that you have to write. We'll do that next.
Is the ownership of an object transitive, like it has children? Do you have also the ownership of the children?
Not by default. So you talk about every single memory location individually.
That the initial object points to, yes.
Right. But we support inductive predicates. So if you want to talk about the whole data structure, you just define this as typically a recursively defined predicate, and then you can talk with just one assertion about the entire whatever list or tree. You can also quantify over memory locations and talk about many locations by just one quantifier.
Yeah.
So in your example, it wasn't quite clear to me. How did you actually encode parallel execution in Viper?
So that's an excellent question. So Viper per se is a sequential programming language. Or maybe I better go here. So we encode concurrency. And in this particular example, I just did that via two method calls. Right? So this looks like they were executed sequentially. And that's okay because I don't have a post condition here. Right? If I had a post condition here, then this would be fishy because then the post condition of left would be available to write, which it shouldn't be. But since I don't, this really corresponds to two fork operations. So give some permissions to one thread, give some other permissions to another thread. So for this particular example, that's a valid encoding. But you're right, you always have to encode fork and join via inhale and exhale operations.
So you talked about acquire release semantics of C11. There are 2 or 3 more. Could you say a couple of words about the other memory model semantics that are introduced in C11?
Yes, so as I said, I mean, we specifically do not claim that we have a verification technique for C11, right? We just take the logic that others developed and show that we can encode it. So that logic also supports relaxed accesses, for instance, but it's very weak. So basically, it's almost like release acquire where the invariant is always true. And so we looked at a couple of examples and tried to, that go beyond release acquire, for instance, relaxed accesses, and tried to verify them in RSL, and we didn't get very far. So then one would need a richer logic. Such richer logics exist, but I cannot make a statement yet whether we can encode them in Viper. We are reasonably optimistic, but I have no evidence so far. You want to correct me, Alex? Go ahead.
I was just going to say, they have a follow-on paper at DMPI this year, which introduces reasoning about memory fences and relaxed atomics. So the logic is still not in any sense complete, but this we can also encode. So we have at least some reasoning about some programs that use relaxed atomics.
Okay, more questions? Okay, no more questions. Let's thank Peter.